In lecture 3, we'll continue with our discussion about supervised learning. So in the previous lecture, we started talking about supervised learning and we mainly introduced linear regression, which has been part of the material has been discussed in the applied linear regression class. And we also talk about regularized linear models and polynomial models. And in today's lecture, we're going to continue the discussion of linear models. But here, our main topic is to introduce a new optimization method or algorithm that give us the best parameter beta we're trying to find for linear regression. So the main topic is about the algorithm called gradient descent, and there are different versions of gradient descent. One is the batch gradient descent, the other one is stochastic gradient descent, and also there's a combination of the two gradient descent methods. So we'll have a third discussion about gradient descent, and then we're going to talk about a very important method to detect underfitting, overfitting. So the method is called learning curves. There are a few different occasions about learning curves, and here our application here is to detect overfitting and underfitting. And then we have a small topic which is about early stopping. And this is about iterative methods where you can find a certain point at which you should stop training your model anymore. Otherwise, you will overtrain your model, which leads to overfitting model. And the last one, we're trying to actually move our topic to classification. It's also supervised learning, but our goal is not for predicting numerical values. It's more about solving classification problems, right? Like the spam and non-spam emails. So we're moving to logistic regression. And in the next lecture, we're gonna continue this line of discussion to talk about classification methods. All right, so let's move back to the main topic, which is about gradient descent. The gradient descent method is a very widely used method in machine learning. And later on, we'll talk about neural networks and deep learning. And you can also see this method is widely used also there. And this is not a machine learning method. It's an optimization method, but it's widely used in machine learning. So we'll introduce the method here. So the idea here is we have a cost function like the RSS residue sum of square for linear regression. And suppose this is for the linear regression, the RSS cost function, right? The parameter that we want to solve for, or the minimizer we want to get is the beta. So cost function in the linear regression is a function of beta. And we want to find the beta that minimizes the cost function. So we would like to get this particular beta here, and we denote this particular value of beta by beta hats. And we can find this by normal regression, by the normal equation. And there are some disadvantages related to normal equation. First, the main disadvantage is it takes a long time to evaluate or to solve the inverse, although we actually don't explicitly find the inverse for x transpose x inverse. Right? We have a term x transpose x inverse, right, for the normal equation. Right? Although we don't explicitly find inverse, because finding inverse is really expensive in linear algebra, but we actually solve a linear systems. But still, the problem can be very expensive. Right? If you think about it, you have a lot of features. Right? When you have a lot of features, right, X transpose T will be a very long matrix. So X transpose times X will be a square matrix that is that has a very large size. So this part can be very expensive. Right? So solving normal equations is hardly used in real applications, right? Because it's just too complicated, too expensive. Right? Although the equation is really simple, right? But evaluating the um, answer or trying to solve the linear system is really expensive. So here we develop a new method called gradient descent. So this is a very um, good graph that can illustrate the steps of gradient descent. Right? This is an iterative scheme, which means you have to start from somewhere. That means you need to have an initial guess. Right? Suppose our initial guess is here. That's our beta 0. That means we start from this particular beta. I guess this is my solution that minimizes the cost function. So the corresponding cost function value is here. And obviously, this is not the solution. This is not the minimizer, right? It doesn't minimize the cost function. Then what we can do at this point, we can evaluate the slope of this point. The slope tells us since it points the south east, right? That means the slope is actually less than 0. Right? The slope here is less than 0. And what we do here is along this direction, I suppose I move my original beta 0 downhill, right? This is like a hill. We're going downhill. So I move, when the slope is less than 0, I move my points downhill by a certain step size. Right? So why do I move from here to here instead of from here to here? Right? I have a step size that controls how much further this point goes. Right? So, but the general idea is I'll move downhill. So I move here. At this point, I evaluate the slope again, and it tells me it's again less than 0. So I'm still going downhill, and how much I go is controlled by the step size. Suppose I move my point to here, right? And again, I can continue this process. Every step, the slope is less than 0, right? So just move downhill until I hit the minimum point or around the minimum point where my S will be equal to 0. If it's near the minimum points, then S should be close to 0, not exactly 0. And then I will be done, which means I find a particular beta hat that minimizes this cost function. And this is the idea about gradient descent. I suppose I'm on this side, then what happens? If I'm on this side, then this is my initial beta 0. And I evaluate the slope. The slope here tells me it's greater than 0. So that means actually I'm uphill, right? If I move this way, this is uphill, this is downhill. Then I need to move, right, the opposite way. Okay, so it's controlled by a certain step size, so I move to here. And this point, I'll move to here. And this means if your slope is less than 0, you will move this way. If your slope is greater than 0, then you move this way. Right? To here, to here, to here, eventually you will hit the minimum. And so this is the gradient descent method. And we talk about the size of the step, right? The size of the step actually has a particular name. It's called learning rate, right? Which is also a very important parameter in gradient descent. And why is this important? We can consider two cases. The first case is when the learning rate is really small. That means for each step, you only move a little. So move a little, move a little, move a little. It takes really large number of iterations. One iteration means you move one step. It takes a large number of iterations to hit the true minimizer here. And later we will see for one iteration, the cost is really big. We can't afford too many steps. So we may give up because it already costs a lot of computational time or computational resources. So we may just stay here and we cannot move anymore because we run out of computational resources or time. So this is the risk of using a very small learning rates. And what happens if we have a relatively large learning rates? For large learning rate, you will see something like this. First, you are here, right? You know you will move, since the slope is less than 0, you will move this way. You will move this way. And since your learning rate is too large, that means your step size is too large, it can move to here. After it moves to here, right, and we have a slope which is greater than 0, right? Then you move to here. Move this way, and since your step size can be large, it can move to here, or it can move to here. It can cause the oscillation. That means you are, since your step size is too big, you are on the downhill direction and uphill direction, which means the solution is oscillating around the true minimum, and it never moves to the true minimum. This is an example of showing this. Right? It's better if we look at the starting point here, right? We use this as beta 0. Right? Since the slope is less than 0, it moves to here. It actually crosses the true minimum. And since the slope is greater than 0, then you move to here, then move back to here. So you can see it moves further and further away from the minimizer. This is the risk of using a very large learning rate or step size. And another case is where you have a function that is not so nice. For this cost function, again, this is called something like convex function or convex cost function. Right? So what this means is if you connect any 2 points, right, it doesn't intersect with any of the points on the curve. So this is called a convex function. And this is a nice cost function, right? This means if we're using the gradient descent, if you control the size of the learning rate, you will eventually get to the minimizer. It's guaranteed, right? If your learning rate is not too big, which also means you can wait long enough because you're using a small learning rate, you're using a lot of computational time. And we may have some bad function like this, right? This is definitely not a convex function because, for example, you can connect these 2 points, you can see there's intersection with 2 other points on the curve. So this is not convex. So in this case, we may have a few scenarios. For example, if you are, you start from the this point here, right? If you use a small learning rate, and eventually it can get to here, right? Because at here, s is equal to 0. It will stop. But it's actually only a local minimum because you look at the graph, right, what's the global one, which is the point that's lowest. Right, it's here. This is the global minimum. But you only converge to a local minimum. That's not what you want. Right? This thing can happen. Another thing that can happen is you start from somewhere which is pretty flat, and you will see it takes really, really, really long time, right, to converge to global minimum. It doesn't mean that it will not converge to the global minimum because it's very flat. And if your learning rate is not that large enough, it will just stay on this plateau for a very long time until you run out of running time. Right, so for the convex function, there are more bad scenarios where you cannot get to the global minimum. But for the convex function, you can see there's only one global minimum. Right, so this is the general introduction about the gradient descent method. Right, then we'll talk about the first method for gradient descent. It's called the batch gradient descent. So the batch gradient descent basically means you use all of the data, you use all of your training data to find the gradients. Here, the gradients basically means slope. In the first, in dimension one, we call it slope. Right. So for example, we have a function f of x where x is a scalar. Right? F prime of x, where we write it as df dx. Right? That's the slope. Right? It's actually the first derivative, and we also call it gradients. Right? If you have multiple input, let's say f of x1, f of x2, then in this case, right, you cannot just take first derivative, right? We're taking partial derivative, first partial derivative, and the collection of the first partial derivative, we call it gradients. So what we do here is we denote this by this, right? This is a nabla, and it means gradients, right? The gradients of f, it's equal to a vector. First element of the vector is df dx1. That represents the slope toward the x1 direction, and df dx2, right, that represents the slope along the x2 direction. Right, so for multivariate function, we use gradients, and the gradients means the collection of all the first order partial derivatives. All right, so for example, if we look at the partial derivative of MSE beta, right? MSE is RS as residue sum of square divided by n, the number of data points. Right, so minimizing RSS is the same as minimizing MSE. Right, so suppose we're minimizing MSE beta, then we need the gradients of MSE beta. Right? MSE is the cost function. Right? You need the gradient. That means you need the direction. So you know whether it's you move this way or right, you move this way. So we need the gradient. For the gradients, that means we need all of the partial derivatives. Right? Partial MSE beta, partial beta j. For the beta j term, when we evaluate the partial derivative directly, we can get this. Right? You can check why is this true, right? This should be very easy to check. Right? From the form of MSE. Remember, MSE is 1 over n, sum I goes from 1 to n. Right? Then you have yi minus beta t xi square. Take partial derivative with respect to beta j, just one of the, you can write this as sum of beta j xij. Here j goes from 1 to n, right? S goes from 0. J goes from 0 to n. Right? Then you can take partial derivative, you should get this. And this is just one term. We collect all of the first order partial derivatives, right? Then we get the gradient of MSE. And the gradient of MSE in matrix form can be written as this. Right? So later in homework problem, right, you will check whether this is true. So this is the gradients. Right? After gradients in 1D, it's like you have the slope. Right? Then you will know how to move your beta points, whether it's to the left or to the right. Right? For multidimensional, there's no meaning to talk about right or left. Right? But that actually, you know the direction of the moving. So how we move our beta is like this. Right? This is from right? Analogous to the first, to dimension one, where you have f of x. F is the cost function, where we call it j of beta. Right? Let's say j of beta, just the beta scalar. Right? If beta, the derivative is less than 0, then you move right. Right? So in this case, that will be beta. Since your derivative is less than 0, let's write the derivative here. We do partial j, partial beta. So you want to do a minus because you want to increase your beta. Moving to the right means increasing your beta, right? So you use a minus and you use the step, we call this eta. So eta times partial j, partial beta, partial j, partial beta gives you a negative number. So eta is a positive number. So this is less than 0. Eta is the learning rate or step size is greater than 0. So the product is less than 0. So beta minus a negative number, that's a positive number. So beta will be increased. Right, same thing here. If beta originally that's here, right, then your partial j, partial beta, that's positive. You want to reduce the size of beta, moving it to the left. So this part is positive. This part is positive. Positive times positive, that's a positive number. So beta minus a positive number, so beta is decreased. Right. So this is how we update our beta based on the on dimension 1. So same thing here. We'll do something very similar to this. It's just here we have the gradients. Right. So beta is a vector of all the beta values. Gradients, this is also a vector, right? This is a vector minus vector, right? This is a 1D vector, 1D vector, 1D vector. This is a 1D vector of elements that has elements from beta 0 to beta n, right? Same thing, right? Partial MSE, partial beta 0, partial MSE, partial beta 1, until partial MSE, partial beta n. And elements of n+1 terms, right? A vector of n+1 terms. Eta is just a single number, and you update beta in this way, you get the new beta. Same as this, right? And then from here, you get the new beta. Right here, beta new means the updated beta. All right, so this is the batch gradient descent. Here, when you calculate, right, the beta here, you will need to calculate the gradients, and the gradients can be shown to be in this matrix form, right? So, and why can this take a relatively long time? Because you can see you have X transpose, X beta, right? This is a matrix vector multiplication, vector subtraction, matrix vector multiplication, right? So if your sample size is really large, then it could give you a long time to update your beta. And also you have to store all of this data in your system, right? If your data is really large, right, you may not be able to store all of the data, right, in your memory. That can be another problem. So we can look at example 1. Let's look at example 1, which is a revisiting of the example 1 in lecture 2. And if you recall, what we did there is we define a number of data. We generate 100 data points, and we let X to be the randomly generated uniform number between 0 and 2. And we suppose the linear regression relationship exists and y equal to 4 plus 3 times X. Right, and then we give them Gaussian noise. Right, so this is how we get the data. So the linear regression relationship, the beta 0 term, that's 4, beta 1 is 3. Right, then we generate the X matrix. Right, that means we add a column of 1 for X. right? This is our X matrix when we use the normal equation. And here we set the learning rates. Learning rates, suppose is 0.1, and we set number of iterations, 1000. That means when you move your point or beta closer and closer to the minimum, how many steps you can afford. You cannot use many, suppose you cannot use many iterations, right? Then you just set the maximum number of iterations that you can afford. And we set that to be 1000. And we start from some randomly generated number. So this beta here, they're randomly generated from a normal random variable. So we just randomly start from this beta here, and then we'll let the algorithm do the job by itself and move closer and closer to the true minimum. So we'll do a for loop, right? So this is we can only afford at most 1000 steps. So we'll do a for loop where each iteration is a one step of the gradient descent. So first to compute the gradients formula is here, right? X transpose times X beta minus Y. So you can see this is X transpose times dots means matrix multiplication, X times beta minus Y, and divided by n time multiplied by 2. Right, so this formula is just this formula here. And then we update beta using this formula here. Beta equals beta minus eta times the gradient. And then at the end of 1000 iterations, then we print out the beta. The beta values are around 4 and 3. It's very close to the true number beta 04 and the beta 13. Right, so actually the method works. And also we can check what we get using the normal equation. So we just call the normal equation from the last lecture, and we print it out. It's the same number, we can see. It's the same number. Right, so this means the batch gradient descent method actually works, and it gives us the same value as the normal equation. At least they are the same up to this is 6 digits, right? After 8 digits after the point, right? Same thing here, right? After a few digits, right? Maybe 10, maybe 12, definitely they should be different, right? But at least this tells you the two method actually they're equivalent. All right, and here we try to look at the effects or how the learning rates can affect our learning results, right? So here we work on the same problem, right? Still the same data. We don't change the data. Still the same data, and here we use 3 different eta: 0.02, 0.1, and 0.5. So this one is pretty small. This one is pretty big. This is like middle, right? So we'll see the different effects. And similar to the previous lecture, we used the subplots and we set up the subplot ID. Here we use 1 row and 3 columns. So it's the first position is 131, second position 132, third is 133. Right, then we set the number of iterations to be 10, where we don't run a lot of iterations. And again, we start from some randomly generated number. This is our starting beta. And then we make 3 plots, right? So this is for range of length of eta 3. So we make 3 plots. We first plot the subplots, right? Give us empty subplots, and we do the tight layout so you won't see this axis, y-axis, x-axis overlap. And we give them a title, right? The title is eta. You can see the $ eta because the Matplotlib provides the functionality for making some latex printouts, right? Or latex editing. So this means eta is a latex command that gives you the leta letter, and you put them, let them surrounded by this $sign. This means this LaTeX command. So this give you eta, then equal. This is a percent 3.2f. This means you let this is the formatting, right? String formatting. So this means the whole thing here will be a floating point number with 3 digits and 2 after the decimal points, 2 digits after decimal points. And what is this number? This number, so this part will be replaced by this number here after it using the percent sign. So in the first iteration, 0, that means 0.02 will be substitute this part. 3 digits, 1, 2, 3, 0, 0, 2, 3 digits, 2 after the decimal points, 0, 2, right? 2 after the decimal point. So that would be just a 0.02. For the second iteration, 0.1, 3 digits, 0, 1, 0, 2 after decimal point, that's 1, 2, 1, 0. So you got 0.10, then you got 0.50, right? That's the title. Then you first plot the data, x, y, dot, color equal to b. These are the scattered data, scatter plot of the data. And then we plot the lines. Right here, the lines, what are the lines? We use 2 points. One is 0, x equal to 0. The other one is x equal to 2. Since 2 points will decide a line, so we look at the beta 0 plus beta 1 times 0 and beta 0 plus beta 1 times 2. So we get 2 points here. One is a point here. The other one is a point here. Right? These 2 points will give us a line. So that's how we plot a line. And we set it to be red. This is our starting line. We use the initial beta. So that's our initial line. You can see this is far away from a nice regression line. And then we up the data step by step. Right, that means we've copied the beta. So beta init.copy, that means you are making a copy of the beta init vector. And we store it in beta. Right, we don't want to do beta equal to, if you're new to Python, right, this will give you some other consequences if you're doing this. Right, that means if you do this, beta equal to beta init, if both beta and beta init are 1D vectors, then this will be the value of beta, right? If you change the value of beta init, then you will also change the value of beta. Right? This is because this is assigned, the value of beta is assigned by reference. It's like if you're familiar with C language, right? They use the same pointer, right? They point to the same place, then it will just refer to the same value. Then if you change beta, if it needs beta underlying init, then you also change beta. So we don't want to do this. We want them to be independent. So we let beta be a copy of beta init. So beta and beta init right now, they're independent. For the first iteration is equal to 1. And now we let the while loop run. So we'll do the first iteration, second iteration until the 9th iteration. Then we have 10 lines here. Right? So for each iteration, we first compute the gradient, then we update the beta. For gradient, we use the formula. Betas, to update the beta, we still use the formula we just discussed. Then we plot out the line. Again, we use the point 0, point 2, 2 points, we make a line. And you can see these green lines, we use the green color. These green lines are the regression line as we update the beta. Don't forget the iteration equal to iteration plus 1. Right? Then if you don't do this, you have a dead loop, right? Which means it runs forever. So for the 3 different cases, we can see for the first one, since it's too small, so you can see this is your initial line, then you move up, move up, move up. After 10 steps of the iteration, you still don't have a very good regression line. So this means your learning rate is too small.
The other extreme is you pick very large learning rates. So this is your initial line, then you will see a divergence, right? The second iteration, your line is here, next your line is here, next. Since your learning rate is too large, then it's just it doesn't go to the minimum, right? It will oscillate between the minimum and actually it diverges in this case. In this case, we're illustrating a nice beta. So our initial beta, then the next step, and we can see after about a few steps, like 5 steps, we already got a very nice regression line, which means the beta is already very close to the beta hats, right? The true minimum. So this illustrates the effect of learning rate. It can't be too small. For it to be too small, then your iteration will be, the convergence is really slow. It can be too large. If it's too large, then it can diverge. You will never get the true minimum. So it has to be of a good size. And how to get a good size, right? In practice, we'll do a grid search, right? Which means we pick a lot of beta and we see which one is the best. Right? We will talk about grid search in a later lecture. But now here you should understand the effect of the learning rates. All right.
The second type of stochastic gradient descent is called stochastic gradient descent. So this is a little bit different from the batch gradient descent. And here, for each step, we're not using the whole data set, but only pick one entry or one data point. And we use that single one data point, or we call it an instance, right, in the training set. Just one data point, we use it to compute the gradients. Then we, based on the computed gradient, then we update the parameter value. Right, so this is called stochastic gradient descent. And usually we just pick this the particular instance just randomly. So this has some advantages. You can think about the advantage, which is one of the advantages pretty obvious. That means each time you only need to use one instance, which means you look at the data size here. If you're looking at this matrix here, right? X has only one row, right? So the data, the amount of data here is pretty smaller, like X, right? Just one row. This is a one row of data, right? Times a column data, right? And also not only the involved, the algebra involved is less computationally extensive, but also think about the memory requirements. You don't need to load all of the data into your memory. You only need to load one instance of the data at one time. So it also saves a lot of memory. Okay, so computationally, this is definitely advantageous compared to the batch gradient descent. But the disadvantage is you will see some irregular behavior, right? Which means if you look at the batch gradients, you start from here, then you move to here, move to here, move to here until you reach the minimum, right? But for stochastic gradient descent, since each time you're just using one of the data, right, which is quite random. It involves a lot of randomness. You won't see this constantly goes down. Maybe it goes up, right, or goes to the other side, right? Then goes to here, maybe goes to the other side, right? If you have more complex shape, something like this, right? This may jump to here and again jump to here, and goes down, jump to here, right? Something like that. So it's much more irregular, right? And this sometimes can be good because when you jump from here to here, right, you actually can avoid being trapped to the local minimum, and instead you will achieve the global minimum. That could be a good thing. And what is bad is supposed to look at this case here. As you
use stochastic gradient descent and getting close to the this is the global minimum in this case, right? You won't see it settle down here, right? This is, you still see a lot of oscillation, around this global minimum. Right? That's also something you don't want to have. So there's something to take this into consideration, right? So we know these disadvantages and how we can avoid these disadvantages. There's something called learning schedule, right? Which means how you can schedule the learning rates. The learning rate can be a variable, right? It can change from time to time. So the general idea here is initially we can set a relatively larger learning schedule. The relatively larger learning schedule can make the learning faster. And also it can help the stochastic gradient descent move to the, for example, in this region, you will get the local minimum, right? It can use a large learning rate. It can help the point move to the other parts of the graph. So it may be, move to the region where the global minimum is located, right? So that's the advantages of using large learning rates at the initial steps. And as we move on, that means as we use more and more iteration steps, then we hope the iterates, they will settle down. For example, it's in this region, and you just follow this down. This is the downhill gradually, right? And then we hope to use a smaller learning rate. Right? This helps that when the solution is close to the global minimum, it doesn't oscillate too much. Right, so we have a learning schedule like this. If we have a plots of the learning schedule, sorry, not learning schedule, this is the eta, right, the learning rate with iteration steps. We'll just call it T, right? T means iteration steps. So we'll have something general like this, not a straight line, right? It can be this, right? It can be functions like this. Gets with the number of steps, then the learning rate gets smaller and smaller. So there are different ways to define learning schedule. We'll introduce one we used here. And you can also find what are the learning schedules defined in scikit-learn, right? So we'll talk about that. So we'll also look at example 1. And here we don't use batch gradient descent, we use stochastic gradient descent. Right? That means each time for each step to compute the gradient, we'll only use one data point or one instance. And we do it by runs of 100 iterations because we have 100 data. So for one run, that means you use 100 data. So that's one round. Right? So one round has 100 iterations. That means 100 steps. Right? One data gives you one step. So one round has 100 iteration. And this one round is called an epoch. And we'll do more than one epoch. So for example, we do 50 epochs. Right? So we define a number of epochs, so 50. So how many steps we're doing? We're doing 50 times 100. That's 5,000 steps. 5,000 steps of iteration. Right? And here, remember the batch gradient descent method. Right? It's iterated 1,000 times, right? Because we set the iteration number to be, we did it here, right? Set the iteration number to be 1. And right, but here we only do it 50 times. Right? That's the number of epoch. For the number of epoch of the previous case, right? That's 1,000. Right, here we do it 50 times, so that's 50. And then we'll compare the the results, and whether we get a result which is closer to the larger number of epochs. Right. So here we set the number of epochs, that's 50, and we define the learning schedule. And here our learning schedule is, so in this case, we define it as T0 over T plus T1. At T0, we use 5, and for T1, we use 50. So we use this. T here is the number of steps or number of iterations. I use one data, we get one step done, or we get one iteration done. So we updated our beta. We use another data, right? One iteration down. So T is the number of iterations. So as the number of iterations grow, then we can see the denominator is T plus 50. It gets bigger and bigger. Then this is equal to eta. Eta becomes smaller and smaller. Right? That's our learning schedule. Right? There are 3 or 4 different learning schedules defined in scikit-learn, right? And later I will point the function that where we can see what kind of learning schedule they used in scikit-learn. Right? It's definitely not unique. Right? You can define anyone that has a decay for the learning rate. So what we do is still we do a initialization of the beta value. Then since we do 50 epochs, so we do the first iteration is about the number of epochs. And for each epoch, what we do is we use all of the 100 data. Right? So we do 100 iterations for each run. That means for each epoch, we do 100 iterations, 100 steps. So for I in range n is 100. What we do is we randomly pick a data. Remember, we do it randomly. So we generate a random number. We use it as an index. So random numpy.random.randint. Randint generates random integers. So this gives you a random integer between 0 to n minus 1, right? Python doesn't include n. A lot of Python functions doesn't include the final number. So it's between 0 and n minus 1. Right? That means if it's 0, that means which one you will use to update your data or update your beta. I will use the first data point or first instance in my training set, right, to compute the gradients and then update the beta. If I pick if it's randomly picked as 1, that means I use the second entry or second instance. Right? So first I random pick a data. So I just extract that row, right? X random index, right? I pick that row. That means I use that data. I call it xi. The corresponding y is just yi. So I only use this xi and yi, simply one row of the data, simply one number of your target value. Still, I use the gradient formula, nothing changed. Still, I use the, and then I update my eta, right? Epoch times n plus I. So initially, what is it? Epoch is 0. And 0 times n is 0, and I is 0. Initially, learning schedule here, the input is 0. So it's just a 5 over 50. So initially, we use 0.1. And later, it gets smaller and smaller as epoch goes up and as I goes up. Right? So epoch times n plus I is the number of iterations. So I update my eta, the learning rate, and I update my beta. Right, then I'm done. After the 2 layers of iterations are done, then we're done. Then we print out the final results. So we print out the beta, and it's 3.96 and 3.13. It's very close to 4 and 3. So you get good results. Right? So no need to 1,000 iterations, and for each iteration use all of the data points. Right? No need to do that. Right? We just do 50 epochs. Right? For each epoch, I'm doing 100 iterations. That means using all of the data. And we get similar results. And you can see what's the convenient part. The convenient part is here. Right? The data is really light, just one row of the data. Right? It can be easily fitted into the memory. Also, the algebra involved, it doesn't matter whether you have very large number of features, right? It still can be accommodated. But if we're using the batch gradient descent, you can see you have to load all of your data into the memory, right? To compute x transpose dots x dots beta. Right? This can be a huge burden for your system. Right? So this is good for something we talked before, out of core learning. Or when we talk about online learning, right? We don't have to fit all of the data into the memory, right? As data gets available, we'll just read in the data and train our system or update our hyperparameters of the model. Right. So one thing you may think about is, why do we just randomly pick one, right? If you randomly pick one each time, for the 100 data points, where some data may be picked multiple times, right? Actually, it doesn't matter. Especially you have a large number of data in your data training data sets. First, if you have large number of data, for one entry, if it's randomly picked like 5 times or 4 times, the chance is really small, right? And the second is that the algorithm doesn't really care if it picks a certain data point multiple times. So one thing what you can do, you can also make sure for one epoch, and you do in this case, you do 100 iteration. You can make sure you pick the data without any repetition. That means you guarantee that each data point is picked just once for each epoch. Right? What you can do is, right, suppose this is your data, right? So you have 100 rows. You can do a shuffling of the data. Right? Later, you get a data. Let's use this to mean the new data where you have done the shuffling. Or maybe the first to go to the last, the second to go to the middle, or a third to go to the second, and so on. After do a shuffling of the data, you just pick the data one by one for each iteration. That's also okay. Right? But it has been shown that in real applications, this will converge slowly. So we're just randomly picking a certain instance at a time. All right, and all right. So to do this thing, right, for linear regression, right, we can, for example, if you don't want to solve the normal equation, right, we can actually use the stochastic gradient descent, for the for solving the linear regression problem, right? And what we can do is we use the SGD regressor. All right, we uploaded SGD regressor, the very first cell, right? Saying sklearn linear model, right? Suppose we use the gradient descent to find the beta hats in linear regression, right? We first import the SGD regressor, and then we construct the SGD regressor object, right? We can set the maximum number of iteration, right? This is the number of epochs. So I do 1,000 epochs at most. After that, it doesn't matter whether it converges or not. Right? I'm done. And I define the tolerance, that's 1e minus 3. Right? That means the system or the code will monitor the job of the cost function. if the job of the cost function, right, if it's less than 1e minus 3, right, which means it's pretty small, right, then it just stops. Right, so this is the tolerance. Where this is the stopping criteria for the gradient descent. And here penalty, I let it be none, which means I don't do any penalty. I'm just doing regular or ordinary least regression, least square, and I don't do any penalty. I don't do any regularization. I don't do L2. I don't do L1. For example, for ridge, you can set L2, and you can set L1 for lasso regression. All right, so here penalty equal none. That's just the ordinary least square. It's just a regular regular linear regression. And here, my initial learning rate, I set it to be 0.1. And you can also set the learning schedule. Right here, we define learning schedule here. You can check this function here, the SGD regressor. On the web page, you can see there are a few different learning schedules defined there. Right, and you can see it's quite similar to this, although it's not the same. Right? You can see they have different names for the different learning schedules. Right, so we'll just use the default one. Right, if you want to know the detail, please go to the website of this this function, right, the menu of this function. So after I construct my SGD regressor, then I can simply call SGD rec.fits, right? It's very similar to how you use the linear regression or ridge regression or lasso regression. Call the fits. This is your X data, right? This is your Y. These are features. This is your target value. And let's look at intercepts, right? We just print out the same thing. We can print out intercept at beta 0. We can print out beta 1 to beta n. So that's coefficient. In this case, we only have a beta 1. Right, so it shows that we get 4, close to 4 and close to 3. We still get very good results. Right, similarly, if we're doing a ridge regression instead of regular regression, we just set penalty be L2. We can also set the maximum number of iteration where we use the default one. I think the default is 1000. You can set the tolerance. You can just use the default one. Here we use the default one. You can set the eta initial learning rates. You can use the default one. But here we use everything as default one. Only set the penalty to be L2. Right here, actually L2 is the default one. If you check the menu of this function. That means we want to do a ridge regression. We want to use stochastic gradient descent to estimate the beta hat. And then we do a fit, same use, and we can do a predict. Right? You can print out for example, you can also print out the coefficients to see the coefficients. And here we do a predict. We look at what's the predicted value for x equal to 1.5. Go back to the data here. Corresponding to 1.5, that's around here. 1.5 is here. The value should be around 8, right? And it gives us 8.8. Right? That makes sense. Right, so this means for linear regression, we can not only use normal equation. That's what we did before for when we use linear regression class. And we can also use the SGD regressor to learn the parameters or coefficients of linear regression or regularized linear regression by using stochastic gradient descent. And this has an advantage when we have a large number of data. Right? Also, sometimes we want to do it online, do online learning, and we want to do the SGD. So again, we have a middle ground, which is called the mini batch gradient descent. So this is a combination or compromise between a batch gradient regression where you use all of the data sets for each step and the stochastic gradient descent where you use only one instance, randomly picked one instance to calculate the gradients. right? The mini batch means not use all of the data for each iteration, not use just one. You can use, for example, 5, for example, 10, which is which we call a mini batch, right? Just a small random sets, but not one, not both extreme, not all, not one, or just a small sets, which is randomly picked. And this is called the gradient descent. So you can think about it's like the elastic net, which is a middle ground between lasso and reach, right? The gradient descent, it inherits both advantages of the batch gradient and also the stochastic gradients. Like I think about the advantage for stochastic gradient is computationally inexpensive. Same here, although there's multiple instances of data you use each time for the iteration, but you use only a very small set. It can still fit into the data. It's still easy to evaluate the gradients, right? So it inherits the advantages of stochastic gradient descent. And compared to stochastic gradient descent, for mini batch, it's more regular, right? We mentioned for stochastic gradient descent, since we only use one instance of the data each time, and can jump here and there. It doesn't like constantly converges to the minimum point, the global minimum, right? But using mini batch, you won't see too much about this irregular behavior, right? It acts more regularly compared to the stochastic gradient descent. So that's something we also do in practice. We just combine both the stochastic gradient descent and the batch gradient descent. We call it mini batch gradient descent. All right, so we're pretty much done with the gradient descent method. This is a very useful method, which is good for online learning, good for a large number of data points, large number of feature, and we'll see this used again and again in the future. And the next topic, we want to switch gears. We want to talk about learning curves. Right here, we want to answer the question that's how can you decide whether a certain model is overfitting or underfitting? Right. For example, if you have a simple model, then you can plot out y equal to f of x, where f is your model. Then you can visualize whether you have a lot of wiggles, whether the model is kind of complicated that tries to fit too much for your training data. Right. Like we watched before, like we saw before, right? For this example here, this is what we did in lecture 2, example 3. I use a high degree polynomial to do this. You can see this, maybe it's for another one, which is more linear, and not this one. But you can see it tries to use a high degree to put all of the points or most of the points on the curve. Right? Sometimes you can use your eyeballs to see that. But for example, if the model is complicated, it's multidimensional, right? How can you decide whether it's underfitting or it's overfitting? Here we want to do something, introduce something called the learning curves. And here we want to introduce the idea using example 3 in lecture 2, where we have this data sets. We generate 100 data X, remember that's from uniformly distributed between -3 and 3. And y is a quadratic function. Right here, the constant term is 2, linear term is 1, coefficient is 1, quadratic term it's 0.5. And we added some noise. Right? So we have this quadratic form. And here, we want to plot out a learning curve. Right? A learning curve means we want to make some plots that is represented by 2 curves. Right? One is about training. This is about the training data. The other one is about the validation data. And the x-axis is about the training data size. And the y-axis is about some score. Score is some measure of how well your model is. For example, let's just say we use mean squared error. Right, we have talked about the mean squared error. That's the difference between yi and yi hat. Y hat is predicted from the model. And we square them and sum them up divided by the number of data. Let's just use MSE, for example. So we want to plot out this thing. Right, so we'll use this example here to illustrate 3 different cases. Right, the first case is we use just a linear model, and we know the linear model is kind of it's underfitting, right? Because it's too simple. It doesn't represent this curve, right? The quadratic form. So we know it's underfitting, and then we want to see if we make a plot like this, training score versus the training data size, and the validation score versus the training data size, and we'll see what it likes. Right, so this code does this job. Right, this code here, I'll explain what this code does. So we define a function called plot learning curves. So we want to plot these 2 curves. One is about training, one is about validation. And the input is the model, right? The model is a general. You can, for example, if we're using a general linear model, you can use a polynomial model with degree 5, degree 10, degree 20, and so on, right? So you can input the model that you want to use. X and Y, they are the data, right? All of the data. So what we want to do, since we have training and validation, so we need to split the data first. So we want to split data into training data and validation data. So there's a function which is very convenient. We also imported this function in the first cell. So it's called the train test split, right? So here what it means is we split X and Y. They are the data, the features and targets. We split them into two parts. One is the training part, the other one is validation part. And how many data are in each part. So here I specify, I use 0.2, that means 20%. 20% of the data are test data or validation data. So I have 80% as the training data. Right, then there are 4 outputs, right? The first 2 outputs are about the training X and the validation X. Right? That means I use 80% of the rows of X as training data. I use 20% of the rows of X as validation. The next 2 outputs are training Y and validation Y. So again here, 80% of the Ys, they are in the training data, 20% they are in the validation data. So this test size equal to 0.2 specifies the size of the test data. So this is randomly picked, right? So every time when you run this, you will get a different result because of this is randomly picked. Right, so this is a very useful function where you can divide your data into training and validation. Right, so we'll collect the training error, we'll collect the validation error. Right? The training error, validation error means the MSE. Right, so later we'll plot them. So that's why we collect the training error and validation error. So we do a for loop. The for loop is from 1 to the number of training data. Right, for example, we have 100 data in this case. Test data has 20 entries. For validation, for training, we have 80 instances or 80 data points. Right, so here the length of X train is actually equal to 80. So this means 1 to 79. That means we use 1 data, we use 2 data, 3 data, 4 up until 78. And for each of the data size, 1, 2, 3, 4 up until 79, we will calculate the model. First, we'll build the model. We'll train the model. Right? That means we train the model, use the corresponding data. and then we find the prediction. Right, this is the prediction for the training data. And then we use the model to predict for the validation data. And after we get the predicted values for the training data, predicted value for the validation data, then we can compute the errors for the training data and the errors for the validation data. That means the MSE for the training data and MSE for the validation data. They are the Y values. And how to compute the MSE? We can import the mean squared error data. It's imported in the first cell, right? You don't need to calculate this by yourself, although it's pretty easy to do it by yourself, but you can use the built-in function. So we use the built-in mean squared function, mean squared error function. This is for the training data, predicted training data, and the original Y values for inside the training data. So we already know these Y values for the training data, but these are the predicted using the model. So this will give you the MSE, and we do append. That means we put it inside this, append this inside this list. Same thing for the validation data, right? You have the value for the validation data. You also predicted Y values using the model you built. So this gives you a mean squared error. You also append it into the validation error. So now after the for loop is done, you have all the values that you want. So make two plots. One is the red line, which is about training. So it's square root of the training errors. This is mean squared error. Actually, I should put RMSE here. I put RMSE here. This is the not just MSE, but it's the RMSE, root mean squared error. So that's why we take a square root here. Root mean squared error, it will give you this, this for the training. So it give you this red line. And mean square, root mean squared error for the validation error, it give you the blue line. All right, we use R and B, that means red and blue. For the line style, one is just a straight line, the other one is straight line with a plus. You can specify the line widths. You can also give it a label. So later when we do a legend, it shows training and validation. X labels the training data size. It goes from 1 to 79. Right? From here, we know it goes from 1 to 79. And this is the root mean squared error. All right, so let's see. All right, so we have defined this function, then we will plot these two lines, right? What we first do is what model we want to input. We just use linear regression. That means we don't use any polynomial features, just the linear regression. So the model is sklearn.linear regression. And we know X, we know Y, right? Then we just specify these three inputs: linear regression, the X value, the Y value. Make sure the X value is in 2D. Your X is in 1D. And make it 2D. So this gives us this plot. All right, so what this plot means? This plot means initially look at the red data. You only use 1 or 2 data to fit the linear regression. It gives you an error of 0. That makes sense, right? For example, 2 points will decide a line. If you only have 2 data, it decides a line, a linear line. So both of the points are on the linear line. So your training error is 0. Right? But as you increase your data size, right, your learning linear model cannot learn the data perfectly, right? So the error will go up. But at a certain point, right, it will not go up anymore. It hits a plateau. That means when you increase more learning data, right, you cannot increase your model performance, right? This is because later we'll talk about this, right? This is because there are 3 parts of the errors related to your model, related to learning, machine learning model. But one part is irreducible error, which means there's some variability in your data, which can be reduced, right? For example, the measurement data, right? Maybe there's some outliers of your data. So this this kind of uncertainty is inside the data. So no matter how large your data size is, you cannot reduce that part of the error. So no matter how you increase the training data size, it doesn't drop anymore, right? The MSE doesn't drop anymore. And look at the validation data. Initially, since we only use 2 data points, right, for the training data, so it cannot generalize well. So for the validation data, it's pretty bad. The root mean square error is pretty large. And later on, we increase the data size, so it's generalized better and better. Okay? And so it drops until a certain point, and it becomes plateau. Right? It doesn't matter how you increase your data, since your model cannot learn the data perfectly from the training data, right? You will not, the validation data, the error will not drop anymore either. All right, so we'll see this. This is a prototype. This prototype is training data goes up and the validation data goes down, and there's a very small gap between the training error and validation error. And another characteristic of this is the MSE is pretty large. Remember, this value here is about 1.5. Right? This is a typical behavior of underfitting. Right? To make a comparison, we'll go back to this. Let's look at the second example here. Right? We can compare these 2 figures, then we know you should better know what I was talking about. So here I want to use a overfitting model. Right? That means we use a higher degree. So suppose we use 10th degree polynomial, and we repeat the same thing. Here we use just the linear regression. Here we use the 10th degree polynomial regression. Right? Let's see what happens. So first, how can we define a model here? Right? To define a model, we use something called pipeline. This is very useful. Pipeline just means we combine several procedures, right, into one function. So this means I want to do for the data, I want to do polynomial feature first. Right? If you're using the polynomial model, you first need to get all of the features, all of the combinations such that their degree is less than or equal to 10. So you need to do the polynomial feature first. After polynomial feature is done, then we can call the linear model. So there are 2 steps. The pipeline combines the 2 steps into 1 step. And the poly features, they are just the names. So look at this, this is actually a dictionary. Right? Index and value, index value. It doesn't matter how you call this, right? But just means the name for the step. That means our first step is do a polynomial feature, second step do a linear regression. Right? Combine these 2 steps, this is a model, right? This is a polynomial model. Right? This is how we do pipeline. Right? For more details, please check the menu of pipeline. So after we're done, we get this polynomial regression, right? This is a pipeline. We can use it as an input. And we use the data X, data Y. After we plot this, right, you will see, you won't see this very well because for the blue line, it can reach very high, right? So it doesn't give you a good visualization about the relative position of these 2 curves. So we just limit the Y values between 0 and 3. Okay, so we can see this graph clearer. And what we see here, we also see as we increase the sample size, training sample size, right? The RMSE gets better and better and until it hits a plateau as we did before. What's different as this plot is, you can see the RMSE, the error for the training data set is much smaller than the error in the first case for the underfitting case. Remember, your underfitting means your model, your model cannot fit your training model well. So you will have a large error. So that's expected, right? Here in this case, it's an overfitting model. That means the error for the training data size is pretty low. For the validation, it also starts from large value. As you increase the training data size, it gets smaller and smaller, and it gets to a plateau. And what's different here is the distance between these two curves is pretty large. This is very small. This is very large. The large gap means what? Large gap means your model cannot generalize to the validation error. So your validation error is much larger than the training error. So now we have two prototypes. Right? One is like this. Right? This is for train, this is for validation. And what's the characteristic? Characteristics is the gap here is pretty small, and the training data error curve is pretty high. This is underfitting. Right. The second prototype is similar, increase, decrease. Let me do this again. So increase, decrease, and the height is pretty low. This means the training, the model fits the training data pretty well or too well, but the gap is pretty large. This is training data, this is validation data. This tells you this is overfitting case. Right? Compare these two plots. It's obvious, right? This is underfitting, this is overfitting. And for what kind of plots you will get a good fitting, right? That's the thing we're gonna see for the third case. In the third case, we use a polynomial of degree 2. We still use the pipeline, right? Transform the features, then call the linear regression. I use the plot learning curve function we define. So you can see the third prototype is also increase, decrease, but the characteristic is the height of the training error is pretty low. That means the model fits the training data pretty well. And also the gap is pretty small. It also means the generalization is also well. So the gap is pretty small. This is a good case, right? It means the overfitting effect and underfitting effect is minimal. All right, so this is how we interpret the learning curves, 3 prototypes. All right. So related to the learning curves, right? We can talk about the errors related to the to generalization of machine learning models. So there are 3 types of errors. One is the bias. Right? The bias just means your model is inaccurate. Right? The accuracy comes from, the inaccuracy actually comes from you're using the wrong model. For example, the data is quadratic, you use a linear model, right, in the first case. Right? So there, that's called a bias. Just means the model is not accurate because you had a wrong assumption, you had a bad visualization of the data or bad insight of the data. The second kind of error is called variance. Right? This means when you train the model, after you train the model, right, you get the model and you perturb the model a little bit, right? Then your model, how much your model varies. That means how much of the model varies means, or the model varies means the coefficients of the model varies. Right. That means when you perturb the data a little bit, how much the coefficients changes. Right? That's the variance. So for more complex models, right, if you change the data a little bit, then your coefficients will change a lot. Right? You can see it from a simple case. Right? Suppose you look at just some data which is close to linear. Right? These are the data. Then what's your, if you use a simple model, that will be this model. If you add one more data point to here, the model will change, not change too much, maybe just bend downward a little bit, but not changing too much. But suppose you are using a higher degree polynomial, right? Then what happens? Okay, let's rewrite the data. And initially, maybe your data is like this, right? Very oscillating to try to include more points on the curve. And now, suppose you have another data. Let's see, the data is here. Right? Then your polynomial may change a lot, right? Because it try to fit or try to force the data to be on the curve, right? Then it can change a lot, right? Something like that. So when you have more complex model, the variance is bigger. Right? That means your model will change a lot with respect to a small variation in the training data. Right? So this is the second part, which is variance. The third part of the error is irreducible error. That means the error is there. You cannot reduce the error. It's just there. There's some measurement data, and during the measurement process, right, some uncertainty can be generated. Right? When someone records the data, maybe just copy the number wrong. Right? There's some irreducible error there. So you can think about the bias and the variance. This part we can ignore it, just there, right? Bias and the variance. Right? Some model tries to reduce the bias more, but it increases the variance. What kind of model? It's the overfitting model. Right? For example, we use a very high degree of polynomial. We try to reduce the bias. We try to make the model more accurate, but the variance increased. We have large coefficients. So it's when the training data change a little bit, right? Then your model will change a lot. Right? So that's the overfitting model. For underfitting model, the bias is pretty large. Right? Because the model is not accurate, but the variance is pretty low, right? Suppose you use linear regression, that's the variance is very small. The coefficients of the model is really small, but it's not very accurate since you have a large bias. Right? Sometimes we're trying to make a compromise between bias and the variance. We're trying to strike the balance between bias and variance. And also another thing is you can think about what is the area here, right? The area here is just the line here is kind of represents the irreducible error. Why can it not continue to go lower with the more training data? That's because you cannot learn a model perfectly because of the learning, the irreducible error, right? So this point here, this line here, it represents the irreducible error. That's the size of the irreducible error. All right, so we're going to move on to another topic, and this is about early stopping. So this is also a regularization method, right? This is for the iterative methods like the gradient descent method we talked about. Right? We start from some initial guess. Right? We do multiple epochs. And when we do this kind of, for this kind of training, we can monitor the training error. We can also monitor the validation error. The training error will get smaller and smaller as the number of epochs goes up. But later, usually we will see is at a certain point, the validation error will not drop anymore. Instead, it will move up. So what this means is after this point, you are actually getting overfitting. You don't train your model anymore. You train your model further, that means you are overtraining your model. You're getting overfitting. Right? Then we should stop here. We use the model parameters, right, corresponding to this epoch as the model. This is the best model. We'll not use the model here. We'll not use the model here. Right? This is called early stopping. Right? Usually you will not see this nice speed here. Maybe after this you see goes up, goes down, goes up, goes down, goes up, goes down. So you can wait for a little bit. and find the minimum point and use that point as the best model. Right? It's called early stopping. The idea is pretty easy. Right? This is also a regularization, right? Which means you don't want to have an overfitting model. You can avoid overfitting in this area by stopping here. Right. So the last part I want to talk about is the logistic regression. And this is related to what we're going to talk about in the next few lectures, which is about classification. So we'll talk about logistic regression. So logistic regression, it has its similarity with linear regression here, because it involves something like this, right? X transpose times beta, right? Similar to beta transpose times X. Both of them are vectors, so it doesn't matter. Right? So it's beta 0 times 1 plus beta 1 times x1, beta 2 times x2, and so on. Right? It involves this. But in linear regression, we use this X transpose beta, right, as our outputs. But here for logistic regression, it doesn't use X transpose beta or beta transpose X as the final outputs. It's just use this number to feed into a function denoted by sigma. This is called sigmoid function. Right? Means it's S-shaped. And actually, we plot out the function here, logistic function. It's S-shaped. And we call this function the logistic. Right? So that's why we call this a logistic regression. You can see the similarity, and you can see the difference. And usually we use this to do classification. Right? For example, whether it's spam email or non-spam email. And the output is interpreted as a probability, right? Because you can see the range of this function is from 0 to 1. So we interpret this value p, the output of the logistic function, as a probability. Right? So then to use this for classification, right, that means if it's close to 1, we say this is a positive class, means it's a spam. If it's close to 0, the p-value is close to 0, then we say it's a negative, which means it's a non-spam. Right, so this is a basic idea of logistic regression, the math, and also how we use this. Right, this is the code to plot the logistic function, right, just this function here. So how do we use, so one thing we can think about how to do this is we still need to train the model, right? To train the model means we still need to get the beta. We have all of this X, we have the function sigma, right? We still need to train this beta, train the model to get the beta, right? And how we can train the model. So we talk about the training and the cost function. Right, so to train the model, that means you have a bunch of X, right? For each X, X1, it corresponds to Y1, can be a 1 or 0, that means the label. Right, X2, these are the features corresponding to 1 or 0. You have all this data, right? Xn, 1 or 0. Right, so for each instance, that means each instance like x1 or xi, if the label is 1, we give it a cost function that's negative log p. And why this happens? Think about y equal to 1. So for y equal to 1, that means it's a positive case. Right? For positive case, we want this p-value to be close to 1. Right? Because we interpret the p-value as the probability. If the probability is close to 1, then it's a positive case, right? It's interpreted as a positive case. So when y is equal to 1, we want the p to be close to 1. When p is close to 1, let's look at the form of negative log p. Negative log p is an increasing function. Negative log p will be a decreasing function. Right? 1 is equal to 1, right? That's 0. And what is the value of p? P is from 0 to 1. right? So we only have this part. This is 0, this is 1. So when p is close to 1, this means the cost here is close to 0. That's what we want. Right? If the case is y equal to 1, if the label is 1, the cost is close to 0. Similarly, if y is equal to 0, the corresponding cost is negative log 1 minus p. And let's first plot out what is negative log 1 minus p. At first, it should be something like this. Right? This is 1, and this is 0. This is negative log 1 minus p. Right? If y is equal to 0, that means we want p to be close to 0. P is close to 0, that's interpreted as y equal to 0. If p is close to 0, then the whole value of the function is close to 0. That's what we want. Right? If we set the cost for each instance in this form, right, then the beta will be learned by causing or by making p to be close to 1 for the first case, or by making p to be close to 0 for the second case. So this is a nice cost function that we can use. And this is just for each instance. For all of the instance, we just add them up, add all of this up. Right? But we don't want to use if and if. What we can do is we can use this nice form. Right? Think about yi equal to 1. The second term will go away. So only have 1 times log pi, and we pull out this negative sign. So you can put it inside. So when yi is 1, is 0, is 1 times log pi, that's negative log pi. So you have the cost function for that particular case. If yi is equal to 0, this term will go to 0. Then you have 1 times log minus pi, and also including this negative, you have negative log 1 minus p. So we now know the cost function for the logistic regression. Then we're going to solve this, but unfortunately, we don't have the closed form formula to find the beta hats, right, for the logistic function. Then what we do here is we can take the gradient. Based on the gradient, then we can use the gradient descent methods to find the beta hats. Right? And after we have the beta hats, then we can use the logistic function to do classification. Right? For example, if you have the beta hat now, and what you want to do prediction, or want to do labeling, right? What we can do is we run sigma beta hat transpose times x. And let's say this is x new, it's some new data, right? This will give you a number between 0 to 1.0. If it's greater than 0.5, for example, you will get positive. And if it's between 0 and 0.5, you will get negative. All right, so this is all. We'll see more examples about logistic regression in the next lecture for classification. And that's all for lecture 3.